Hi guys, this is the first part of a 5-part Docker 101 tutorial. In this video, I'm going to explain to you what Docker is, the need for Docker and what problem it solves, and finally the difference between a Docker and a virtual machine. I've added chapters for simple navigation for each section. Feel free to use it. Alright, let's get started. It all started when Solomon Hykes from .cloud, which is a hosting company now known as Docker Inc., did a 5-minute presentation at PyCon in March of 2013. This was the first time when Docker was released as open source to the community. Check out this video, 5-minute presentation video, and the link is below in the description. Docker is an open platform for developing, shipping, and running distributed applications, whether on laptop, data center, VMs, or cloud. Docker provides the ability to package and run the application in a loosely isolated environment called container. But why do we need Docker now, and what problem does it solve? In the past few decades, we've seen major infrastructure shifts. In the 60s, there were these huge mainframe PCs. With the advent of PCs in the 90s, the first infrastructure wave took place. From traditional mainframe architecture, which had been for like 3 decades here, was converted to a PC distributed architecture by putting in Mac, Windows, or even the DOS at that time, and installing networks using Ethernet cables and TCP protocols. Few years later, not even 10 years, the next shift from data center to virtualization took place because servers were too powerful and utilized the idle time. So we started creating a lot of OSs in a single piece of hardware. This was virtualization. For example, VMware, Hyper-V, and VirtualBox are some of the hypervisors available in the market. The next wave after that is the cloud. Within 5 years after virtualization, we had the cloud starting up on 2007-2008 when Amazon released the AWS solution. That was the first idea we had for easy, cheap, disposable compute power that we could spin up and shut down from a website. This really shifted the landscape to get to where we are now. Then we have the next wave, which is the containers. Containers also include serverless, functions as a service technology, because all these things are made possible by containers. Very soon it will become the de facto and we will be using the containers. Containers are the next wave in the infrastructure tech, and this is a huge shift in the ecosystem. Each wave is happening faster and faster, and it's even getting adopted even faster. So that's why you need to learn Docker now. So as each of these infrastructure wave takes place, migrations is the hardest part. However, the nice thing about Docker tools is that it is created with developer in mind, which means it will work the same for developers as well as the sysadmins, operators, builders, testers, and etc. Now the Docker solves this matrix from hell complexity. You will have multiple types of applications like front end, back ends, databases, workers, all that needed to work together to run the software. Those will have their own dependencies and different requirements running in different operating systems. And then you have different infrastructures running the software in developer, tester environments, data center, cloud, and so on. There's a whole lot of way of doing these things. But the way the containers work is consistent across the board. It allows you to package the software regardless of the operating system. It allows you to distribute the software regardless of the setup. It allows you to run and test the software the same way everywhere you're running it. Maybe in Mac, Windows, PC, cloud, data center, edge devices, and so on. They all run the same way fundamentally when you're using Docker and this makes a lot of pain problems around the software lifecycle much easier to deal with. Now, let us look into what other problem Docker solves and what it doesn't. Docker enables more efficient use of system resources. That is, instances of containerized apps uses far less memories than virtual machines. They start up and stop more quickly, and they can be packed far more densely on their host hardware. Docker enables faster software delivery cycles. Enterprise softwares must respond quickly to changing conditions. Docker enables application portability. Where you run an enterprise application matters behind the firewall for the sake of keeping things close and secure by or out in the public cloud for easy public access and high elasticity of resources. Because Docker containers encapsulate everything an application needs to run, they allow applications to be shuttled between the environments. Any host with a Docker runtime installed can run the Docker container. Now, Docker shines for microservice architectures. One of the software patterns containers make easier is microservices, where applications are constituted from many loosely coupled components. Few problems that Docker doesn't automatically resolve. For example, Docker won't fix your security issues. Software in a container can be more secure by default than software running on a bare metal. Docker doesn't turn applications magically into microservices. If you containerize an existing app, this can reduce resource consumption and make it easier to deploy, but it doesn't automatically change the design of the app. Docker isn't a substitute for virtual machine. This is one of the myths that containers can make the virtual machine obsolete. Of course, many apps that can be run in a VM or virtual machine can be moved to a container, but that doesn't mean all the apps can be moved or should be moved. If you're in an industry with heavy regulatory requirements, you might not be able to swap containers for virtual machines. Okay, I've mentioned a lot about virtual machines and containers. Now I'll explain to you the difference between virtual machine and containers. So, virtual machine and containers have similar resource isolation and allocation benefits, but function differently because containers virtualize the operating system instead of the hardware. Virtual machines are an abstraction of physical hardware, turning one server into multiple servers. The hypervisor allows you to run multiple virtual machines on the single machine. Each virtual machine includes a copy of an operating system, libraries and binaries that can take up tens of gigabytes. This leads to slow boot up time for virtual machines. On the other hand, containers are an abstraction at the app layer that packages the code and dependencies together. Multiple containers can run on the same machine and share the OS kernel with other containers, each running as a isolated process in user space. Containers take up less space than virtual machines, typically in MBs, and can handle more applications and require few virtual machines and operating systems. To sum up, containers have a significant advantage over virtual machines. They require less space, faster boot up time, use less system resources, use less CPU and memory, and share the same kernel. So, in this part, we have learned what Docker is and why you need to learn Docker right away. Docker also solves the matrix of hell problem, and I've also shown you the difference between a Docker and a virtual machine. We have come to the end of this first part. In the next part, I'll be explaining to you the Docker engine and the architecture. For all that and more, I'll see you in the next part. Thanks for watching. Please like and subscribe my channel for more videos like this. Bye.
Hi guys, this is the second part of a 5-part Docker tutorial. In this video, I'm going to explain to you about the Docker engine and the Docker architecture. Okay, let's get started. Now, the Docker engine is an open source containerization technology used for building and containerizing the applications. Now, Docker engine acts as a client server application, a server being a long-running daemon process called Docker. The term daemon refers to a background process which in most cases started after the boot up of the host system. The Docker daemon creates and manages the Docker objects such as images, containers, networks, and volume. The Docker client Docker is the primary way that many Docker users interact with Docker. By using commands such as docker run, the client sends these commands directly to the Docker daemon via the REST API. Yeah. Docker is written in Go programming language and uses a technology called namespace to provide isolated workspace called containers. Docker objects such as network containers, images, and volumes will be dealt in the next part. Okay, we know that the Docker daemon does the heavy lifting of building, running, and distributing the containers. This is achieved from a Docker client which communicates to the Docker daemon using a REST API or Unix sockets or an interface. Now, let's take a closer look at this architecture. Now we have three components, a client component, the Docker host where your Docker engine will be installed, and a registry. The fundamental and the most important Docker objects are the images. Docker registry stores these images. By default, Docker host or the Docker engine is configured to look the images from the Docker hub. You can also use your own private registry. So, if an image is not available, commands using docker pull can be executed to retrieve the required image from the Docker hub. It's also possible to use commands such as docker build to be executed using an existing image. When the docker run command is executed, a container is started using the available image. Now, this is a basic workflow of how Docker images and containers are built. So, we have seen the main parts of a Docker engine. We have seen how Docker pull, Docker run commands work via the architecture. And if you're more interested in learning Docker, I recommend you to install Docker system in Windows or Ubuntu system. The link to this is I've attached in the description. And in the next part, I'll be explaining in detail the difference between an image and a container and what a Docker file is, how to manage data in the container, and networking in Docker. Thank you for watching. Until next time, see you. Bye-bye. Hi guys, this is a third video of a 5-part Docker 101 tutorial. Check out my other videos to give an idea of what Docker is and how it is built. In this video, I'm going to explain to you the major Docker objects such as Docker image, containers, Docker files, managing data in Docker, and Docker networks. So let's get started. Docker image is the fundamental object residing in the Docker world. Without this, all the other Docker activities are not possible. An image is a read-only template with a set of instructions for creating a container. It contains source code, config files, environmental variables, libraries, and runtimes as such. Now, to build an image, we need to create a Docker file which has very simple syntax and run it. So, each instruction in Dockerfile creates a layer in the image. A layer is nothing but a file generated by using a command. In this case, from Ubuntu 18.04 is a command, and this generates a layer 1, like so. Now the next command will generate another layer, uh, and so on and so forth until the command is arrived. So while updating a Docker file and rebuilding it, only those layers are recreated. So in this case, I have mistyped the command instruction, and I'm recreating the command instruction and building it so that only this layer is regenerated. This is what makes Docker powerful in comparison with other virtualization technologies. The next object is a Docker file. And Docker file is the method of choice for real-world container deployments. It is systematic, flexible, and efficient to build a Docker image. Here you see an example of a Docker file, and here in the middle you see the commands used in the Docker file. Pause the video here and have a look at the commands. When we talk about Docker file, Docker ignore is another file which will be useful in many cases. We don't want certain files to be stored along with image. For example, API keys, environmental files, etc. To exclude these files, Docker ignore file must be created alongside the Docker file. It plays an important role in creating more compact and faster running containers. In this example, we see the folder .git, node modules, and so on will be excluded while building the image. This works also in similar fashion to git ignore file. So the next object which we are going to see is a Docker container. Container is a runnable instance of an image. This can be accessed by Docker API or CLI to start, stop, create, move, or delete a container. You can connect a container to one or more networks, attach storage to it, or even create a new image based on its current state. By default, containers are well isolated from one another. If you start a container with an image, a thin writable layer will be created. Thin writable because any modification during the lifetime of a container are stored in this thin writable layer or the container layer. We can also start a second container based on a similar image. This way, the containers are also isolated from each other, and it exactly knows which base image to be started from. Containers are defined by the images as well as other configuration options set at the time of creation. When a container is removed, the data stored within the container layer is also removed. That means the data is not persistent. So now I'll show you how to persist the data and what possibilities are available within the Docker environment. To persist the data, Docker provides two options. One is the volumes. Volumes are most efficient way and the recommended way to persist the data. The data resides within the Docker area within the file system. That means the container does not have access to the file system. The second option are the bind mounts. Using this method, the host's file system or directory is made accessible to the container. This allows non-Docker processes to modify the host's file system and could cause unwarranted calls for security concern. Docker also provides the possibility to store data in the host's memory. This is only available within the Linux environment. For example, Swarm Services uses tempfs mounts to mount secrets into the service containers. Named pipe, available only in Windows Docker hosts, can be used for communicating between Docker hosts and containers. Common use case is to run a third-party tool inside the container and connect to the Docker Engine API. So, the next Docker object is the Docker networks. Communication between Docker containers services to communicate with each other or other non-Docker workloads. There are 5 types of network drivers which is shipped along with Docker Engine. Bridge is the default driver and is useful to communicate between multiple containers within the same host. It also provides a possibility to access containers via ports from external network. Host networks are useful when you want to isolate all the other aspects of the container except the networking part. MAC VLAN, on the other hand, assigns unique MAC address to the container and makes it looks like physical host. Overlay networks connect multiple Docker hosts and its swarm scope driver rather than individual hosts. Last but not least, none driver disables all networking and is usually used in conjunction with custom network driver. Third-party network plugins can also be installed and used with Docker. They are available either in Docker Hub or from the third-party vendor directly. So, in this video, we have seen different Docker objects like images, containers, and managing data within the Docker world, and also networking. In the next part, I will show you the basic and important commands to work with Docker. If you like this video, give a like and subscribe to my channel for more videos. Guys, this is the fourth part of a 5-part Docker 101 tutorial. Check out my other videos to get an overview of what Docker is, how it is built, and the major components. I've added the link below in the description. In this video, I'm going to show you the important Docker commands and its working. The commands are build, run, exec, pull, and push. These commands can be executed directly from the Docker CLI or the command line interface. So let's get started. Docker image is the fundamental Docker object. To build an image, we use the command docker build. The docker build command requires 2 arguments. One is the Docker file itself with simple set of instructions containing how the image should look like. And the second one is the context. The Docker file must always be present at the root of the build context. Context can either be path-based or URL-based. While using the path-based context, Make sure the Docker file is present at the root of this path, and all the contents from this path will be used as build context. URL based context could be one of the following. It can be a Git repository from GitHub or even your private GitLab or so on. It can be tarball archive or it can be a file based. The build command can access any files within the context using instructions such as copy. So, while creating Docker images, meaningful names or tags should be given so that it is easier to identify within the teams or even the community. An image name is made of slash separated components, optionally prefixed by registry. Generally, the name format has a registry, optional port number, slash organization, slash image name, colon, optional tag. By default, the registry is Docker Hub, the tag is latest, and the port number is 5000. In the example below, Mongo colon 4.4.2 refers to an image Mongo in Docker Hub with the tag 4.4.2. An image can have multiple names. This is made possible by the command docker tag. Here is the list of possible name conversions. So the next command which we are going to see is docker run. Docker run is the command which converts a read-only image into a Docker container. When Docker run is executed, it generates a Linux container, allocates a file system, mounts a writable layer, allocates a new network interface, sets up an IP address, sets up NAT, and executes the process and captures its output. The commonly used Docker options are detach, container identification, network settings, and so on. The next command is going to be the docker exec. The docker exec runs a new command in a running container. Docker exec can be only used when the container is running, and it is not restarted when the container is restarted. The command will run in the default directory of the container. In the example below, docker exec -it mongo /bin/bash opens a bash terminal within the container name Mongo. The Docker images can be shared with other teams or community using registry. Registry can either be Docker Hub or self-hosted. The registry credentials are managed by Docker login. Docker push is the command used to upload an image to the registry. While pushing the image, progress bars are shown. By default, 5 layers are simultaneously uploaded at a time. The uploaded image can be retrieved by another command called docker pull. Now, the Docker Hub contains many pre-built images. Make sure to have a look at it before building your own image. By default, 3 layers are simultaneously downloaded at a time. Okay, in this video we have seen the basic and most important commands used in Docker. These commands are build, run exec, pull and push. These commands give a general workflow while using Docker. Check out my playlist for other parts of this tutorial series. And also make sure to install Docker, which will be the prerequisite for the next part of this tutorial. Docker in Windows 10 or Ubuntu, you can follow my installation video. I've attached the link below in the description. The next part is going to be a demo where we will see and explore the Docker objects and commands which were covered in the other parts of this tutorial. Thanks for watching. Like and subscribe my channel for more videos like this. Hi guys, this is the fifth part of a 5-part Docker 101 tutorial series. Check out my other videos before proceeding ahead with this part. In this video, I will show you the basic working of Docker using the Getting Started app, which will be followed by a live demo. Okay, so let's get started. So our environment is going to be Windows 10 with Docker for Windows installed. Check out my video on how to install Docker in Windows 10. I've added the link below in the description. I will show you how to get the Getting Started app using Docker, which will then be followed by a live demo by creating a Docker file and exploring some of the Docker objects and commands which we have seen in the previous videos. Okay, I've already installed Docker on this machine, and let me start the Docker now. Make sure if you have some fail symbol already present here, that means your Docker is started. In my case, it's not. So I'll just start my Docker for desktop software. So the Docker dashboard is started. Now, to check whether this Docker engine is running, look at your left bottom corner, and it says started for a while, and it just started running. Okay, now let's just explore what is available. If you're freshly installed Docker for Windows, then you might not see any containers or images like so. Now I'll show you how to get the Getting Started app. For this, I'll be using PowerShell window and copy this command docker run -d -p 80:80 docker / getting started. So let me start a PowerShell window and paste the command and click enter. What Docker is doing here is it's trying to find if an image is locally available. If it's not available, then it tries to get the image directly from the Docker hub or your self-hosted registry. Once the image is getting downloaded, it starts a container since we said Docker run. Now the container is started and has been given an ID 28D8 and so on and so forth. We have asked Docker to publish the internal port 80 to the external port 80. So let's open a browser and see what's available. For this, I'm just typing localhost :80. Okay, we are now in the container and we see an application here. So now on the left hand side, you see our application tab. Just click on this and then scroll down until you see download the zip. So when you click this, you will be asked to download and or open it. So I'll just download it to my desktop here. Once the download is completed, I can just close this window and also minimize these things. Let me just check, refresh it. Here's my downloaded zip file. Now I'll extract the contents of the zip file, extract all. Yeah, now it's extracted. So just go inside the folder and see what are the files and folders available. So first thing we need to do is to build an image. To do this, we need to create a Docker file. Now, I create a Docker file using right click, new text document. and rename it to Docker file. When it asks, yeah, click yes. Now, generally, you can edit this Docker file in any text editor or code editor, and I'll be using Visual Studio Code Editor. You have syntax highlighting and all the lints and test stuff which you can do. So that's why my preferred way of writing a Docker file would be using Visual Studio Code. Now, let's just write some script to containerize or to build an image out of this application. For this, I'm going to do from node. This is going to be a node application. Alpine. I'm going to take the Alpine version. You see, it automatically suggests me the different versions of node available as base image. So now, next thing I got to do is apk add some um, requirements. It's going to be Python, G++, and make. Change the work directory to app. And now copy the contents from this folder, the build context, to the working folder app. Now, once you have copied the content, install the dependencies by using run yarn install only the production tile. The last but not least, start the app saying node src index.js. Yep, now the Docker file is ready. So let's build an image out of this Docker file. Build. Normally, it is enough if you give the path so that at this path we have a Docker file and it builds automatically an image. But it's always recommended to give a meaningful name to the image so that we can find it in the list. Now let me start. Okay, we've created the image now. Let's check the created image. This can be done by using the command docker image ls. So we see here two images. One image was created about a minute ago. That's the image which we tagged as getting minus started. And the other image is the docker slash getting minus started. This was downloaded when we executed the command docker run. Let's also check if there are any containers started or running. And this can be done by docker container ls. Now let me just widen up the screen. And here you can see there's a container which was created 11 minutes back, and it's accessible via the port 80. Okay, to see if to see okay to list all the containers, we use the command docker container ls minus a or minus minus all. In this case, only one container is available, so it's okay. To start a container, we use the command docker run. So now let's use the command docker run and detach the container, publish to the port 3000 externally, to the port 3000 internally. with the image getting started. We could also give a meaningful name for the container by giving minus minus name docker minus one. So when we get a SHA number, it means it's started the container and we don't have any errors here. So let's see whether our app is accessible via the port 3000. In order to do this, I'm opening a browser and just typing localhost colon 3000. Yep, our app is now running in the container. Let me just have some entries here to check whether it's working. Buy milk, study Docker 101 tutorial, check out latest videos from some Ramesh channel, and so on. We have successfully containerized our first application. So until now, we have built an image, started a container, and explored the app. Now you can export or push this image to a repository in order to collaborate with others. Okay, let me now show you why Docker is gaining much attention in the last few years. As I mentioned in my previous videos, the Docker image will build only the layers which have been changed. Other layers will be used from cache. Let me modify this Docker file here by adding a statement. I just expose. We know that we want to use the port 3000, and this expose 3000 will make anyone who's reading this Docker file know that the application will be available at this port. Let's rebuild the image and see what happens. To do this, I'll use the docker build command again and tag it to the getting started image. As you can see here, the layers 2, 3, 4 are used from the cache. This means the Docker does not need to build these layers since they are already available in this file system. Okay, the image is built now. Here we can see there is a significant increase in the build time, meaning um, the previous build time was around about 160 seconds, and now we have here 129 seconds. There's a difference of 30 seconds, and this is a significant build time increase or build speed increase, and we can optimize this Docker files in such a way that we have faster images and faster uptime. We have come to an end of the Docker on tutorial series. I hope you enjoyed it. Make sure to like and subscribe my channel for more videos like this. Bye bye.